Okay, let's talk about a force that powers literally our entire world, but you can't even see it. Electricity. For so many people, it's just this tangle of confusing formulas and abstract ideas. But what if I told you there's a much better way to learn it?
I mean, really, how do you get your head around something you can't see, feel, or touch? When you're just staring at diagrams and equations, it is so easy to feel completely lost before you've even started. You crack open a textbook, and this is what you get: a wall of text. Sure, it's all true, it's important stuff, but it doesn't exactly roll out the welcome mat, does it? It just feels heavy. But here's the secret. What if mastering electricity isn't just about memorizing facts? What if it's about having a really solid plan? Well, in this explainer, that's exactly what we're going to do. We're going to tackle the core ideas of electricity by following a powerful learning blueprint, one that you can use for pretty much any tough subject. So here's our game plan. We'll start with the blueprint itself. Then we'll use it step by step to get a handle on electricity's three main pillars, figure out how circuits work, see it in action in your house, learn how we measure it, and then bring it all home. All right, let's dive in. The way we've structured this entire explainer is based on a simple but super effective learning strategy. You can think of it like a master key that can unlock any complex topic you come across. And here it is, our 5-step plan. It's pretty straightforward. First, you define the absolute basics. Then, you compare the main ways those basic pieces can fit together. After that, you dig into what actually causes things to change. Then, you connect all that theory to the real world. And finally, you learn how to measure the whole shebang. Simple, logical, and it works. Okay, so let's follow our own blueprint. Step 1, the fundamentals. When it comes to electricity, that means there are 3 big ideas that everything, and I mean everything, is built on. First on our list is electric current, which we usually just call I. The best way to picture this is to think of water flowing through a pipe. Current is just the amount of charge, the amount of water that's flowing past a certain point every second. And we measure that flow in amperes, or just amps. Next up, we have potential difference. We almost always just call this voltage, or V. Now, if current is the flow of water, then voltage is the pressure that's pushing that water through the pipe. It's the force that makes the charges move in the first place. No pressure, no flow. We measure this one in volts. And our third pillar is resistance, R. This is basically anything that tries to slow that flow down. In our water pipe analogy, resistance is like a narrow, pinched section of the pipe that makes it way harder for the water to squeeze through. And we measure this in a unit called ohms. Now, here's where it all comes together, and it's actually beautiful. These 3 pillars, voltage, current, and resistance, are all linked by one incredibly simple equation, Ohm's law. It just says that voltage equals current multiplied by resistance. V equals IR. This little formula is the fundamental rule that runs almost all electronics. And this graph shows Ohm's law in action perfectly. Look at this. As you increase the voltage, that's the vertical axis, the current on the horizontal axis goes up in a perfectly straight line. It's a direct one-to-one relationship. And the steepness of that line, its slope, that's the resistance. It's a crystal clear visual proof of V equals IR. Okay, we've got our fundamentals down. Now it's time for step 2 of our blueprint, comparing the core structures. For electricity, that means we need to look at the 2 main ways you can wire things up, in series or in parallel. So on the left here, you can see a series circuit. Just imagine a 1-lane road where all the traffic has to follow the exact same path, one car after the other. Now on the right, that's a parallel circuit. This is more like a big highway with multiple lanes. The traffic can split up, take different routes, and then all meet up again at the end. So what's the big difference? Well, in a series circuit, there's only one path, so the current is the same everywhere. But the voltage gets split up among all the different parts. And if one light bulb burns out, the whole road is blocked. Everything goes dark. In a parallel circuit, though, it's the voltage that's constant everywhere. And the current is what splits up. So if one bulb goes out, the other paths are still open. The rest of the lights stay on. And that right there is exactly why your house is wired in parallel. You want every single outlet to give you the same consistent voltage. You want to be able to turn on your TV without having to also turn on your blender. And you definitely don't want the whole house to plunge into darkness just because one little light bulb gave up. Parallel circuits are what make our modern homes work. All right, on to steps 3 and 4 of our blueprint, analyzing the key factors and seeing how they work in the real world. We're going to take this abstract idea of resistance and connect it to something you probably use every day, your toaster. Now, this is a great question. Think about it. You've got the exact same amount of electric current flowing through the power cord as you do through the little wires inside the toaster that get red hot. So why does one part glow like a furnace while the other just stays cool? The answer is a property called resistivity. It's basically an inherent quality of a material that says how much it naturally fights against the flow of electricity. Copper, as you can see, has a super low resistivity, which is why we use it for wires. It lets electricity flow easily. But nichrome, the alloy used in heating elements, its resistivity is millions of times higher. It is basically designed to put up a fight. And that fight, that really high resistance, is what converts electrical energy into heat. There's a rule for this called Joule's law of heating. The heat produced is directly tied to the resistance. So even with the same current, the high-resistance nichrome generates a ton of heat, making your toaster glow, while the low-resistance copper cord just doesn't. And that's the magic behind toasting your bread. Okay, we've made it to the final step of our blueprint, measurement. We see words like watts and kilowatt hours on our appliances and our bills, but what do they actually mean? Well, it all boils down to the difference between power and energy. Power, which we measure in watts, is how fast you're using energy. It's like your speed. A 100-watt light bulb uses energy faster than a 60-watt bulb. Simple enough. But your electricity bill doesn't charge you for your speed, it charges you for the total distance you've traveled. And that's energy. The unit they use is the kilowatt hour. And get this, just 1 kilowatt hour is equal to a massive 3.6 million joules of energy. That's the number that really matters on your bill. So let's just zoom out for a second. We started with this huge, invisible, complex topic, but we used a simple plan to break it down. We defined the basics, we compared the structures, we analyzed what causes change, we saw it in the real world, and we learned how it's all measured. We didn't just pile up a bunch of random facts, we actually built a mental framework for understanding. We've seen how having a structured plan, a blueprint, can make a topic like electricity totally manageable. The real lesson here isn't just about Ohm's law. It's about the method. It's about how to learn. So the real question I want to leave you with is this. What's the next complex topic you're going to build a blueprint for?